Okay, good afternoon once again. Before I'm going to start, uh, check attendance muna tayo. Okay, so Ryan Cuenca,
Yes, sir. Present, sir.
Jade Delagan. Jade, are you there?
I'm here, present.
Okay, thank you. Uh, Kier Damian. Wala si Kier na. Dina.
Present, sir.
Mary Jean Inyola.
Present.
Okay. Marivic Esteban.
Present, sir.
Thank you. Kim Ganog.
Present, sir.
Noli Magho.
Present, sir.
Thank you. LJ
Present, sir.
Mansanades. Shera May Sorongon.
Present, sir.
Christine Torres.
Present, sir.
Thank you. John Ray Ilianan. Wala na yun. Na si John. Wala na si John Ray. Siya ganina. Well, let's have a review first. In my discussion last meeting, I actually have a review on set theory here. We defined the sample space for a particular experiment. It is the set of all possible outcomes. And then any subset of our sample space, we name it as an event. And we have seen that an empty set is a subset of the sample space. And then the sample space is also a subset of itself. And then we have here two relationships that are very important. Say if we're going to show A is a subset of B. So we have here for the containment, if and only if X is an element of A, that would imply that X is an element of B. And then if we're going to show two sets are equal, that means we're going to show, no, if and only if A is contained in B and B is contained in A, or A contains B and then B contains A. And then we have here some operation, actually operations on our sets. We have the union denoted by this symbol. Okay, the union of two sets. Then we have the intersection of two sets. The complement of a particular set denoted by this. Some book would denote it as A prime. And then we have some examples being illustrated for these set operations. And then we have here in theorem 1.1.4 the properties of sets operation or set operations. We have the commutativity property, associativity, distributive laws. We have the De Morgan's laws. And then I have showed you to prove, say, a particular law here. I think we have proved the distributive property as well as the De Morgan's law. Now, one of the De Morgan's laws. And then we have here the notation for the countable union of events A sub I. Take note that we have a collection of infinite events, A sub 1, A sub 2, A sub 3, and so on and so forth. So we can read this as the countable union of the A sub I from 1 up to infinity. And then the other one, we have the countable intersection of the A sub I I from 1 to positive infinity. And we have again an illustration to this notation, the countable union as well as the countable intersection. And then we have also the uncountable union, no? Of A sub alpha or A sub A, as A is an element of this index set gamma. And then we have also the uncountable intersection of A sub A. A is an element of this index set gamma. Okay, we have here an important definition for two sets to be mutually exclusive or disjoint if the intersection of these two sets is equal to an empty set. And then if we have a infinite collection of events, A sub 1, A sub 2, and so on and so forth, they are pairwise disjoint, or sometimes it is called mutually exclusive if pairwise intersection of these events, A sub I intersection A sub J, is equal to an empty set. That is for all I not equal to J. Again, we have an example below. And then another definition that if we have a infinite collection of events, A sub 1, A sub 2, and so on and so forth, and are pairwise disjoint. So in other words, we have a mutually exclusive collection of infinite events. And at the same time, if we have this countable union of the A sub i's, or these events A sub I from 1 to infinity, to be equal to our sample space S, that would imply this collection of infinite events are exhaustive, because we take the countable union, it is equal to the sample space S. Then this collection of infinite events form a partition of S. So now we're going to proceed to the next section. We have the basics of probability. By the way, before I'm going to proceed, can anybody here define probability? What do you think is a probability? Guys? Just in your own words, say, Nolly, can you define probability to us?
Hello, sir.
Yeah, the word probability.
Sir, sir, naririnig niyo po ba ako?
Yes, Nolly, loud and clear.
Probability, sir, it is a chance that it is a chance of an event or something to occur. That's probability, sir.
Okay, thank you for that, Nolly. So it is a belief in a chance of an event occurring. It's actually a subjective interpretation of the word probability. How about Ryan Kier? Do you have in mind?
Probability, sir, is a likelihood of an event occurring, or if you have the sample space and you have to consider the event in example, it's the number of outcomes of the particular event that is going to be.
Medyo mahina yung boses mo, Kier.
Hi, sir.
Audio.
Hello, sir. Hello, sir. Hello, po.
Siguro next time na lang, Kier. Hindi masyadong marinig. Anybody? How about Ryan? Cuenca?
Hello, sir. Probability is something like a chance or likelihood that a particular event will occur or will happen in a particular situation.
Okay, thank you for that, Ryan. We might say that the probability is a frequency of occurrence, as many would interpret it. But for this section, we have the basics of probability theory. So we're going to define probability not in terms of frequencies, as well as the no, we're not going to interpret also as a belief in an event occurring. We call that as a subjective interpretation. But here we're going to describe it by taking the mathematical axiomatic approach, which is the probabilities that are defined by a function that satisfies the following axioms. Okay, so we have here, as an intro to this section, when an experiment is performed, the realization of an experiment is an outcome in the sample space. So if the experiment is performed a number of times, different outcomes may occur each time, or some outcomes may repeat. So this frequency of occurrence of an outcome can be thought of as a probability. So more probable outcomes occur more frequently. So if the outcomes of an experiment can be described probabilistically, we are on our way to analyzing the experiment statistically. So for this subsection, we have here the axiomatic foundations of our definition for probability. So a collection of subsets of S, of our sample space S, or sometimes called the events of our sample space S, is called the sigma algebra, or a Borel field. So it's being denoted by this symbol, script B. Some book would use script F for this sigma algebra or the Borel field. So if it satisfies the following three properties. So the first property we have that our empty set is an element of script B. And then second, if this event A is an element of script B, then the complement of A must also be in script B. So in other words, script B is closed under complementation. And then letter C, if A sub 1, A sub 2, and so on and so forth is an element of script B. In other words, we have a collection of infinite events, A sub 1, A sub 2, and so on and so forth. Then the countable union. So this countable union of events, A sub I from 1 up to infinity, is also an element of script B. In other words, script B is closed under countable unions. If we're going to get the implication of this definition, it would imply that our sample space S is also an element of script B. Take note that this script B is a collection of events of S. If empty set is an element of script B, the complement of this empty set is equal to S, and based on property B, the complement, it is closed under complementation, then S should be an element of script B. Okay, so empty set is an element of script B. At the same time, the sample space, being a subset of the sample space, is also an element of script B. And then another thing, it implies that it is also closed under countable intersections. No, countable intersections. Say if this collection of countable events, okay, A sub 1, A sub 2, and so on and so forth, is an element of script B, and based on property B, that would imply that the complement of these events are also, no, the complement of these events are also in script B, no, according to property B. So in other words, A sub 1 complement, A sub 2 complement, and so on and so forth. These are events or elements in script B. That is using property B, okay, because it is closed under complementation. And then since script B is closed under countable union, then we have this, okay, the countable union. So this means that the countable union of the complement of the A sub i's, I from 1 to infinity, this is also an element of script B. This according to property C. So if this countable union of the complement of the A sub i's, I from 1 to infinity, is an element of script B, and then according to property B, if we're going to take the complement of that, this one, the complement of that, it is also an element of script B. But according to the De Morgan's law, the complement of the countable union of the complement of the A sub I from 1 to infinity, would be equal to the countable intersection of the A sub i's. So this is also an element of script B. That is why I have said that script B is also closed under countable intersections. Okay? So associated with the sample space S, we can have many different sigma algebras. Now, provided that we have our sample space S, then we can have a collection of subsets or events of S that will form a sigma algebra. So for example, this collection of two sets, ito. So in other words, our script B here, we considered as the set containing containing the empty set as well as the sample space S. This is a sigma algebra because this set script B satisfies the three properties. We're going to check. Is an empty set element of script B for letter A for letter A property?
Yes.
Okay, that's correct. Empty set is an element of script B. If we're going to take the complement of the empty set, we're going to use property B. So S here is the complement of the empty set. It is also an element of B, script B. So property B is satisfied. So if we have letter C, though in letter C we have a collection of infinite events, but this can also be true if we have a collection of finite events. In other words, script B is also closed under finite. When you say finite unions, we have only finite number of events. So we have here the union of these two. The union of these two, empty union S, is also equal to S. So it's also an element of script B. At the same time, if we're going to take the intersection of this, empty intersection S is all equal to an empty set. It's also an element of script B. So in other words, our script B here is a sigma algebra. It is actually the smallest sigma algebra, and we call it as the trivial. It's a trivial sigma algebra. Okay, so the only sigma algebra we will be concerned with, it's the smallest one that contains all of the open sets in a given sample space S. Okay, excuse me for a while. Okay, so I'm going to write here the mathematical definition of an open set for your para lang alam niyo lang kung yung definition niya. Say we have here, okay, a subset A of S is open if every point in A is the center of an open ball contained in A. Okay? So or we may write it in this manner. If X is an element of A here, then there exists a epsilon, positive epsilon, however small, is positive epsilon, however small, such that this interval x minus epsilon and then x plus epsilon, this is an element of A. Say for example, okay, so ito yung ating set A. Okay, or set A. So this subset A of S is open if every point in A is a center of an open ball that is contained in A. So pwede natin sabihin dito, we have here a particular element of A, say this is X. So this is contained in an open ball. That is an open ball that is in A. So we have here sabihin natin we have a positive epsilon here. Pwede natin sabihin dito, you have a positive epsilon here. Maliit lang masyado yung positive epsilon. However small, but still positive. Then this interval x minus epsilon and then x plus epsilon should be an element of this subset E. So kung ito yung x, kung nandito yung x nasa border na part, if x is an element of A here, so that means A is not open because meron tayo kung center yan siya. So we have a ball there that is not contained in A. So all the points must not lie on this sabihin natin boundary of A. Nasa loob lang siya. That is why our A here is an open set. So here we're going to consider only a sigma algebra that contains all of the open sets in a given sample space S. Okay, let's have an example. So if S is finite, if F is finite or countable, then these technicalities, in other words, if S is finite or countable, then we can define our sigma algebra script B to be the set of all subsets of S, including S itself. Or sometimes this script B is called the power set of S. Okay, the power set of S. It is the set of all subsets of S, including S itself. If S is finite, we can define it clearly. We can define it. But if S is countable, somehow we cannot define it using the enumeration method. We cannot enumerate all the elements of that. But if S is finite, then we can enumerate all the elements of our script B. Say, for example, if S has n elements, then there are 2 to the n sets of script B. We can see that in exercise 1.14. So for example, if you consider S here as a set containing 1, 2, 3, no, the set containing the elements of 1, 2, 3, then our sigma algebra script B is the following collection of 8 sets or 8 subsets of S. So we have here the singleton, the set containing 1, the set containing 2, the set containing 3. And then the set containing the 2 elements, 1, 2, 1, 3, and then 2, 3. And then we have the empty sets. And then the sample space is also a subset of our, or rather, is also an element of script B, which is a subset of the sample space itself. So we have 8 elements for our sigma algebra script B. So you can verify, no, we can verify that this script B is a sigma algebra. First, the empty set is an element of script B. Okay, totoo yan. Makita naman natin dito. The empty set is an element of script B. If A, no, if one is an, if an event is an element of script B, then its complement is also an element of script B. Say for example, 1, this set containing 1, if it is in script B, the complement of this, which is the set containing 2 and 3 here, is also an element of script B. If this singleton containing 2 here is in script B, if we're going to take the complement of that, which is actually the set containing 1, 3, should also be in script B. Same thing, if we have this singleton containing 3, then the complement of that, which is the set containing 1, 2, is also an element of script B. You can verify also that if you're going to take the finite unions of this elements or elements of script B, it is also in script B. If you're going to take the finite intersection, since S is finite, so if you take the finite intersection of any of these sets or elements in script B, it is also in script B. That is why script B here is a sigma algebra. It satisfies the 3 properties above. Okay? Understood?
Yes, sir.
Okay, so if S is uncountable, by the way, ito yung kanina, sa example natin, finite siya. S is finite. But we can also consider S to be countable. When you say countable, we can consider the set S, no, containing the set of positive integers 1, 2, 3, 4, 5, and so on and so forth. So S is countable, countable. Then we can form our script B from that set S. In general, if S is uncountable, ito part, if S is uncountable, it is not easy task to describe script B. However, script B is chosen to contain any set of interest. Say for example, our set S here is the open interval 0 to 1. It's very clear that our S here is uncountable. So it's not an easy task to describe our sigma algebra script B. Next example, ito, no? Considering for the uncountable sample space S. Say S is the set, no, this interval negative infinity to positive infinity, we have the real line. So we can have, no, we can describe our script B here. No, script B is chosen to contain all sets of the form. So we have the closed interval AB, we have the open closed interval AB, we have the open interval AB, and then we have the closed open interval AB for all real numbers A and B. By the way, is infinity a real number?
No, sir.
Okay, thank you for that, Noli. So it's actually a concept. Uh, so here we have these intervals for a real numbers A and B here. So that is our sigma algebra script B. Okay, so we are now in a position to define our probability function after defining this sigma algebra. So given a sample space S, and then we have this associated sigma algebra script B, a probability function is a function P with domain script B that satisfies the following. We have the probability of A to be non-negative for all event A element of our sigma algebra script B. And then the probability of our sample space S is equal to 1. And then third property, so if we have a collection of infinite events, A sub 1, A sub 2, that are elements of script B and are pairwise disjoint, in other words, this collection is mutually exclusive, then we have the probability of the countable union of A sub I from 1 to infinity, is equal to the countable summation of the probability of A sub I from 1 up to infinity. So the third property is sometimes called the axiom of countable additivity. It is also true that it satisfies the axiom of finite additivity. Say, for example, finite, we have the finite union of A sub I from 1 up to a particular n, particular n, in which the A sub 1, A sub 2 up to A sub n element of script B and are pairwise disjoints. And that would be equal to the finite summation of the probability of A sub I from 1 up to n. So that means we have the axiom of finite additivity in that case. Okay, so we have here the three properties. In order for us to show that a particular function is a probability function, then we must show these three axioms, these three axioms. That is, the probability of an event in script B should always be non-negative. And then the probability of the sample space should be equal to 1. And then the axiom of countable additivity must also be satisfied. Okay, so in other words, ito ating function. We denote it as P. And then we have here our domain, script P. So if we have a particular event here, which is an element of script B, this is an element of script B. So this is being mapped. So we denote it as the probability of A. So ano yung codomain dapat dito? Yung codomain, hindi pa naman na-define dyan. But later on, you will see that the codomain of this, or the range of this function, we have the closed interval 0 to 1. It will simply say, imply that the probability of an event A should be non-negative. It is greater than or equal to 0 for all, no? For all elements in our sigma algebra script P. Okay, let's have an example. By the way, class, makadungog mo sa saba sa silingan. Can you hear? Naririnig niyo ba yung ingay sa kabilang bahay?
No, sir.
By the way, I think starting to rain. Now, medyo malakas yung ulan. I hope it will not disturb us. Okay, let's proceed. Example 1.2.5. Consider the simple experiment of tossing a fair coin. Okay, we have a fair coin. Assumption is a fair coin. So our sample space here, it is a set containing H and T. H for the heads outcome, and then T for the tails outcome. When you say fair, then means that we have a balanced coin. So that is equally as likely to land heads up as tails up. So hence the reasonable probability function is one that assigns equal probabilities to heads, no, and tails. That is, we defined our P here, function P, and such that the probability of this event containing the heads, or H, is equal to the probability containing the event, the probability of the event containing T. Okay? Based on our assumption that it's a fair coin, then we have this equality of probability. Okay? We have this symmetric interpretation of probability. So based on our axiom 1, if S here is the union of the event containing H and then the event containing T, okay, we can see clearly, that the probability of this union will be equal to 1. And since these two events are disjoints, these two are disjoint, then the countable or the finite union of this probability would be equal to the finite summation of the probability. So we have here. And then we have this implication now that the probability of the event containing H plus the probability of the event containing T will be equal to 1. And then considering these two equality now, then we can show that the probability of the event containing H is equal to the probability of containing of an event containing T to be equal to 1/2. Guys, medyo malakas yung ulan.
Sir, clear pa naman.
Clear pa naman. Okay lang. Okay, so this is for the case when we have a fair coin. But if the assumption, if we have an assumption that if we do not have a fair coin, then we can still define our probability. Our probability P based on our actions. Say for example, we have an unbalanced coin in which the probability of getting the event containing H to be equal to 1/9, then clearly the probability of an event containing the tail will be equal to 8/9. Taking the sum of this probability to be equal to 1. Umuulan ba dyan sa inyo?
Tato nga.
Wala pa, sir. No, sir. Init.
Mainit sa iba. Dito sa Iligan, ulan. No? Malakas masyadong ulan. No?
Makulimlim na dito, sir.
Oo. Okay, let us proceed. Theorem 1.2.6. By the way, this theorem here, it actually gives us the common method of defining a legitimate probability function. So we let S here to be the sample space containing S sub 1 up to S sub n. So it's a finite set. And we let script B be any sigma algebra of subsets of S. And then we let T sub 1 to T sub n be non-negative numbers that sum to 1. Then for any A, which is an element of script B, we define. Okay, so we define the probability of A. Okay, so this is our probability of A. This is our definition. To be equal to the summation of, it's the finite summation of P sub I, small p sub I, such that I here, the set of all I, such that the S sub I here is an element of A. So the sum over an empty set is defined to be 0. So if you have an empty set, then the probability of that empty set is equal to 0. And according to this theorem, then P is a probability function on script P. And this is also true if we take S to be a countable sets. Okay, so you can refer to the book for the proof of this theorem. Let me proceed now to the next example. Okay, so we have here the game of darts is played by throwing a dart at a board, dart at a board, and receiving score corresponding to the number assigned to the region in which the dart lands. For a novice player, it seems reasonable to assume that the probability of the dart hitting a particular region is proportional to the area of the region. Thus, a bigger region has a bigger probability of being hit. So referring to this figure, 1.2.1, we have a dartboard. So we have these regions. We have actually the inner circle here. That's for the region 5. And the next circle, which is also outside the inner circle, that's region 4, and so on, for the region 3, region 2, and then region 2. Then according to this figure, the circle has radius r. Okay, radius r. So obviously, the distance between rings is equal to r over 5. So if you make the assumption that the board is always hit, so even though we have a novice player, but we assume that the board is always hit, then we have the then we can define our probability P here, P scoring I points to be equal to the area of region I over the area of the dart board. Okay? Say for example, if we consider the point 1, or in the region 1, scoring 1 point for region 1, itong part na to. Okay. Based on our defined function P, so the probability of scoring I points to be equal to this fractional expression, the area of region I over the area of the dartboard. Clearly, the area of our dartboard here is pi r squared. So the area of the region 1, would be the difference of the two areas. Say, first we're going to consider the area of the whole circle. This pi r square, and then minus the area of the region, or the circle containing the regions 2, 3, 4, and 5. So if we're going to consider that radius of that circle, that radius is equal to 4r over 5. So taking the area of that circle, containing regions 2, 3, 4, and 5, then we have here pi, and then times the radius, which is 4r over 5 square. And then if we're going to simplify this, we have here this numerical value, 1 minus the square of 4/5. So it is easy to derive the general formula. So the function P of scoring I points, then we have here the formula in determining the probability, I from 1 up to 5. Notice that in our formula, in our function P, it is independent of pi and at the same time r. And it says here, according to exercise 1.8, says here that our defined function P here is a probability function. So if you want to show that this defined function P here is a probability function, then the three axioms must be satisfied. First one, the probability of any event A should be non-negative. Next, the probability of our sample space S should be equal to 1. And then, if we have a pairwise disjoint or mutually exclusive finite events, then the probability of the finite union of these events should be equal to a finite summation of the probability of these events. It's actually an exercise, 1.8. So I hope that you're going to, that you try to check this defined function P to be a probability function. We do not know. Maybe this problem will come out in your exam. Okay? Is that clear?
So, yes, sir.
Yun lang.
Yes, sir.
Tatlo, no? Papakita niyo yung tatlo. Hindi na masyado yun. Okay, so we are done with defining our probability function. So let us now proceed to the calculus of probabilities. Somehow it will discuss, this subsection discusses the properties of our probability function. Okay, so theorem 1.2.8 says here, if P is a probability function and A is any set in script B, then it says here that the probability of an empty set is equal to 0. The probability of any event A should be less than or equal to 1. If we have defined P as a probability function, the probability of A here, we have seen that in our definition, it is non-negative But in this property, in this theorem, the probability of A should also be less than or equal to 1. And then third property, we have the probability of the complement of A will be equal to 1 minus the probability of A. Okay, let us go through with this proof. As I have known in our last meeting, some of you are not really that well versed in the different kinds of proof, the direct proof, the indirect proof, proof by contradiction, proof by contrapositive. So here, let us try to prove this theorem. So we start with property letter C. Okay, we know that A and the complement of A are disjoints. And at the same time, if we're going to take the union of this, it is equal to S. That is why A and its complement will form a partition on the sample space S. So S here is the union of A and its complements. Since we know that the probability of the sample space is equal to 1, based on our definition of our probability function, and at the same time, using the third axiom, these two events are disjoints. Okay, these two are disjoint, then the probability of the finite union here, the probability of the finite union of A and complement of A will be equal to the finite summation of the probability of A and the probability of A complements. So if you're going to use these two equalities, 1.2.4 and then 1.2.5, then we can show that the probability of A complement will be equal to 1 minus the probability of A. Okay? Knowing that these two are equal. Ito nasa left-hand side, it is equal to 1. Ito, parehong expression, nasa left-hand side din, equal to this sum of two probabilities. This is why property C is proved. Okay, next. Property B. Since the probability of A complement is non-negative, that's according to the definition of probability function, that would imply that the probability of A should be less than or equal to. Okay, so alam naman natin na ngayon, the probability of A complement here, 1 minus the probability of A, and according to our probability function, the probability of A complement is non-negative. Okay, non-negative. So from here, ang implication nito, this would imply that the probability of A is greater than or equal to, making this inequality. And then for the first property, S is equal to S union an empty set. And then S and empty are disjoints. And we know that the probability of S here is equal to 1. And then using axiom number 3, so the probability of the finite union of S and empty, which are actually disjoint events, would be equal to the sum, the summation of finite of the sum of the probabilities. So if we have this equality, then that would imply that the probability of an empty set will be equal to 0. Okay, these are the first three properties of our probability function. Let's proceed now to the next theorem. If P is a probability function and then A and B are any sets in script B, then the probability of B intersection A complement will be equal to the probability of B minus the probability of A intersection B. Then secondly, the probability of the union. So in this second property B, we have no assumption that A and B here are disjoints. So if we're going to take the union, though the probability of the finite union of A and B here, it will be equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. And for letter C, if A is a subset of B, then the probability of A is less than or equal to the probability of B. So let us prove, we're going to prove these properties. So to establish A, note that B here is equal to this union of these two sets. By the way, you can verify this using a Venn diagram, or you can verify the equality of these two sets using the relationship that we have reviewed a while ago regarding equality of two sets. Pwede naman ganun. Or we may start by saying that B here is equal to B intersection S. B is a subset of S, so B intersection S will just be equal to B. And then we can take our S here to be the union of A and the complement of A. So A and the complement of A disjoint, mutually exclusive, and at the same time exhaustive, equal to S. And then using the distributive property of intersection over union, then we have B intersection A, pwede nga ganun, union B intersection A complement. So we have that. Okay? We can verify that these two sets, note, no? Itong dalawang set na to, itong set na to, at saka itong set na to, these are disjoint. No, these are disjoint sets, or mutually exclusive, disjoint. So we're going to take the probability on both sides. So the probability of B here will be equal to the probability of the union of these two sets that are disjoint. Since they are disjoint, we can apply now the axiom, no? The third axiom in our probability function, and that would be equal to the sum of their probabilities. Okay, here. Sum of the probabilities. So, from that, A is satisfied. You're going to rearrange this, then we can show now, so makita natin itong part, that the probability of B intersection A complement will be equal to, did we just transpose this expression on the other side of our equality? So, next, we're going to establish property B. The probability of the union of A and B equal to the probability of A plus the probability of B minus the probability of the intersection. Okay, again, we can use this identity. The equality of two sets here. Direct na siya, no? gagamitin kaagad natin yung identity. Though we have not yet proved that these two sets are equal, or these two expressions are equal. So as I have said, we can use our definition for showing the equality of two sets, or we can make use of a Venn diagram. It says here, no? A Venn diagram will show why these two expressions are equal. But we can show the formal proof for that. We can also start with this. We take our B here to be equal to B intersection S. Argument lang tayo. Equal yan. It's very clear. Because B is a subset of S. So the intersection, and then up. Sorry. Baliktad pala tayo. Union dito sa pangalawa pala tayo. A union B here to be equal to A union B, okay? And then intersection S. And then after that, A union B, intersection, we can take S here to be A union A complements. And after that, hmm? Oh, yeah. Okay. Next, we can show that this is equal to A intersection A and then union B intersection the A complements. And finally, we have A union B intersection A complement. Here we have that. Okay, notice that A intersection B intersection A complement are disjoint. Okay, here, this set here, intersection this given set here, will be equal to an empty set. So these two are disjoint. So if we're going to take the probability on both sides, we have here the probability of the union of A and B will now be equal to the probability of A. Supposedly, we have here the probability of A. Tama pala to. Okay, the probability of A plus the probability of B intersection A complement. And using the above result in property letter A, then we have the probability of B intersection A complement is equal to this. Hence, property B is being proved. For property letter C, if A is a subset of B, then we have here A intersection B will be equal to A, since we know that A is a subset of B. And therefore, using the property A, then clearly we have here the probability of B intersection A complement is non-negative, and that will be equal to the probability of B minus the probability of A. And then showing now using this equality, this and this, it would imply now that the probability of A is less than or equal to the probability of B. Okay, any questions or clarifications for the proof of this theorem? Yes, LJ? LJ? What is your question, LJ?
Sir, from theorem 1.29,
Ah,
from theorem 1.29, 1.2.9. Katong duha ka set, sir, na A and B, sir. Are they disjoint, sir?
asa dapit nga part?
Sa theorem 1.2.1.
Theorem 1.2.
Above na, sir. Tama, sir.
No. In
They-
theorem 1.2.9, we have no assumption that these two events, A and B, or sets A and B, are disjoint. Is that your question, LG?
Yes, sir.
Yeah, no assumption. Yes, Anoli?
Sir, yung sa theorem 1.2.8,
Okay.
di ba sir yung probability of A complement is equal to 1 minus the probability of A, and it is
Mhm.
greater than or equal to 0. Tapos sir,
Okay.
if
Ay,
yung probability of A complement is 1
Tama,
minus
tama.
probability of A, so dapat sir yung probability of A, sir, dapat less than or equal to 0 siya, sir.
yeah,
I want-
thank you for that. Thank you for that. Itong part na to, since we have here no 1 minus the probability of A greater than or equal to 0, greater than 0, this case, we have here actually, no, the probability of A, the probability of A should be negative probability of A is greater than or equal to -1. Okay, since if we're going to multiply both sides of the inequality by a negative number or negative integer, then the sense of inequality will be changed. So ito pala. Thank you for that, Noli. Hindi ko na-check na. So it should be less than or equal to 1. Okay, thank you for that, Noli.
Thank you rin, sir.
Hindi ko agad nakita. Who else? Wala na yata. So to end, no, this this class, let's consider this last theorem. Theorem 1.2.11, if P is a probability function, okay, if P is a probability function, then the probability of A is equal to this countable summation of the probability of A intersection C sub I for any partition C sub 1, C sub 2, and so on and so forth. Take notes. We have a collection of infinite events here, C sub 1, C sub 2, and so on and so forth. And then the probability of the countable union of A sub I from 1 to infinity, it would be less than or equal to the countable summation of the probability of A sub I. For any sets, again, we have a collection of infinite events, A sub 1, A sub 2, and so on and so forth. So in this case, for letter B, property, the collection of these events, A sub 1, A sub 2, these events or this collection, these events are not mutually exclusive, and at the same time, not exhaustive. So, yung specific, no, yung specific na example of property B here is actually the property B also in theorem 1.2.9. Yung probability ng A union B equal siya sa probability of A plus the probability of B minus the probability of A intersection B. So that would imply for these two events that the probability of A union B is less than or equal to the sum of the probability of A plus the probability of B. So we call this as the Boole's inequality. Say, for example, for the property letter A here, say this is our sample space S. And these are our events, C sub I. Ito, C sub 1. Ito, C sub 2. And then we have here, C sub 3. Okay, C sub 4. Dot, dot, dot. So we have a collection, no, of infinite events, C sub 1, C sub 2, and so on and so forth. When you say it's a partition, the intersection, this collection are mutually exclusive, is mutually exclusive, and at the same time exhaustive. If we're going to take the union, it will be equal to our sample space S. So if we have event A here, kunwari itong event A natin dito, yan part na yan. Say this is our event A. Clearly, we can take our A here, yung A natin, to be equal to A intersection C sub 1. Ito yung part na yan. Ito. Tapos, union A intersection C sub 2. Ito. And then, we have the union of A intersection C sub 3. Yan apart. Hindi na masyadong and then, say union of A intersection C sub 4. Obviously, the intersection is empty. Take the union. And so on and so forth. Okay, so kung makikita nyo yan dyan, yung itong mga naka-shaded na part, ito sila mga part na to. Yung green, yung violet, yung orange, yung brown, yung mga sa regions na yan are disjoint. And this is why we can take the probability of A here to be the infinite summation, the infinite summation of the probability of A intersection C sub I from 1 up to infinity. Okay? So for letter B here, I'm thinking of giving you this as one of your problem set. So, hindi pa yan final. Bibigay ako ng PDF para sa first problem set. But iniisip ko na ito na pwede siguro ito as one of the problem in the first problem set. Okay? So we're done with the properties of the probability function. Next meeting, again, review lang actually yung mga properties. You have taken this in your STT 131 undergrad. Same thing with the next section. We have here the counting principles. Still a review on your STT 131. But I'm going to discuss this. So as of the moment, since it's already time, before we go, are there any questions or clarifications regarding the review on the probability function? Properties, definition of probability function. We start with the sigma algebra, okay? And then we define our probability function, which is a function on this sigma algebra. Okay, and then after that, we have these properties of the probability function. Any questions or clarifications? Are you still raising your hand, Noli?
No, sir.
Wala na. Okay. No questions so far?
None so far, sir.
Okay, so sino yung kanina na pag-check ko ng attendance wala? So present na ngayon si John Ray. Actually,
Yes, sir. Present po.
una yun si John Ray. Si Kier. Yep, si Kier. Nandun si Kier. Okay, so present lahat. Okay, so that's all for this afternoon. I'm going to send you again the PDF of my discussion at the same time the video recording. And that's all, and class are dismissed.
Thank you, sir.
Thank you, sir. Keep